Okay, so in this video I'm going to run through some of the objectives that you would have been working with in ALEX, and I'm also going to run through a practice quiz. So it's also important to realize that at the end of the video lectures for every section, I always run through the ALEX objectives associated with that section of the book. So if you want to see me working through more practice problems, even if you just skip to the end of the video lectures, you can always find that information there. So this first problem is about understanding how atomic size varies across the periodic table. And the important thing to recognize is that elements get bigger as we go down a group, and they get bigger as we head right to left across the periodic table. So if you put all of that together, they get bigger moving from fluorine to francium on the diagonal. Okay, so let's look at our first sequence, and we're asked to put them in order of decreasing size, which means we're going to start with the largest and we're going to end up with the smallest. So the three elements that we have are neon, beryllium, and carbon. And what we realize is that they are all in the same group. So all we have to think about is that they're going to get bigger as we head to the right, which means they get smaller as we head to the left. So we're just going to put them in the order. To get smaller is just going to be left to right. So it's going to be beryllium, carbon, neon. So not too bad. Okay, let's move on to the next series of three. And here it gets a little bit interesting because we have an ion. So we've got sodium and magnesium, and then we also have the magnesium ion. So what we know is that the elements get smaller as we go left to right. So we know that sodium will be bigger than magnesium. But where does Mg plus fit in? Well, if you take a magnesium atom and it has 12 electrons, and then you remove one from it, you would end up with a magnesium single positive cation. Now the electron is being moved from the outside of the atom, so it's going to be making that smaller. So what that means is that Mg plus will be smaller than Mg. So cations are always smaller than the atoms that they are made from, and anions are always bigger than the atoms that they are made from. So this sequence will be sodium, magnesium, magnesium plus. Okay, so in the next sequence we have bromine, chlorine, and the bromide anion. So we're heading down a group here. So getting smaller, we know that bromine is going to be bigger than chlorine. So we've kind of got the order of two of them, but what about this bromide business? So bromide forms when we add an electron to bromine. So bromine normally has 35 electrons. If we add another one to make the bromide ion, so it has 36 electrons, it's going to get bigger, right? Because we're adding something to the outer edge of the atom. And so what that means is that bromide is bigger than bromine, which is bigger than chlorine. And so what you want to take home here is that anions are always bigger than the atoms that they are made from. So the sequence for this will be bromide, bromine, chlorine. Okay, sometimes people will get the order reversed on these. We want these going from biggest to smallest. You need to be kind of like aware of that and not make that error of getting them in the reverse order. So this question is about drawing the Lewis dot diagram for a cation. So hydrogen, here it is, has atomic number 1. So that means that it has 1 proton and also 1 electron. So the hydrogen with a single ion with a single positive charge will have 1 proton and 0 electrons. So when it comes time to place the dots around the hydrogen cation symbol to indicate the number of valence electrons it has, well, it doesn't have any valence electrons. so it gets no dots. So that's kind of easy. There's no dots to place. Okay, so this question is all about predicting and naming ionic compounds formed by two elements. So there's only going to be monatomic ions present, right? Now, ionic compounds form when a metal transfers electrons to a non-metal. So what we're looking for to see if an ionic compound forms is that we have the presence of a metal and a non-metal. So this periodic table that I've got here is colored so that the metals are yellow and the non-metals are sort of that greenish color. So it should be pretty easy to figure this out. So lithium is definitely a metal, and then iodine is a non-metal. So yes, they can form an ionic compound. Chlorine is a non-metal, and then rubidium, not ruthenium, rubidium, Rb, is a metal. So yes, that can form an ionic compound. Iodine, we know, is a non-metal, and then magnesium is a metal, so that pair can form an ionic compound. And then finally we've got lithium, which is a metal, with calcium, which is also a metal, so therefore no, they can't form an ionic compound. So that's 1/3 of your points, right? So now what you've got to do is you need to identify what the name of the compound is. So I like to do the name before the formula, and it's for a really easy reason. Is sometimes the formula, if I do that first, it can kind of betray like what the name's going to be. It can lead me down the wrong path with naming it. So if I do the name first, it's just going to be very, very, it's just a kind of like a way of making certain that I don't accidentally name it incorrectly. So remember when we name ionic compounds, and we're going to do this 3 times for the first 3 combinations there, we give the cation name, and then we give the anion name. Now, in our case, these are cations and anions that are not polyatomic. So what that means for us is that our cation is always going to be of the form where it's just the element name, and then if needed, we'll put the charge in parentheses. Now, there are 3 groups that don't need the charge in parentheses: +1, +2, +3. Group 1A, Group 2A, and Group 3A, those metals don't need their charge indicated, along with silver, cadmium, and zinc. So we want to keep that in mind. So that's something that's important. So maybe it needs the charge in parentheses. Now when it comes to naming monatomic anions, we just take the stem name, which is why I've got the list of stem names here, and then you add the ending IDE to the end. So you probably want to get a list of these like stem names, and you can get those off the internet, or you can take a photo of your book and save it as a PDF, whatever. But you want to find out, you want to get one of those lists. Okay, so let's have a look at this. Lithium is in group 1A. I've already got that circled, so it's just going to be plain old lithium. And then the anion that's combining with it is iodine, and so it's going to be IOD followed up with ide. Okay, that's easy, the first one. The next one, the metal, is rubidium, and rubidium is also in group 1A. There it is right there. So it's just going to be rubidium. And then the anion it's being combined with is chlorine, so the stem is chlor, so it will be chloride. Okay. The next one, the metal, is magnesium. Now magnesium's in 2A, so again, no Roman numerals. Magnesium, and then what it's being combined with is iodide. So we know that, or iodine, and we know the stem name for iodine is IOD, so it's iodide. Okay, and then for our last one, we don't have to do anything because we've identified that it doesn't form an ionic compound. All right, so now we're going to move on to the formula. But before we do that, what I want to point out is that it's important to recognize that we never use the numerical prefixes when we're writing the name of an ionic compound. So that's kind of important, right? Never use the numerical prefix when you're writing the name of an ionic compound. And that's why I kind of like to write the name first, because if I have the formula, I might be tempted to put a di or a tri or a mono in there. But if I just write the name first and remember never to use the Greek prefixes, I won't be betrayed. Now, the other thing to keep in mind is that we're using IUPAC systematic names. So if you just like Google the formulas for these things, you're probably going to get non-systematic names. And so you can't kind of always rely on that being correct. You might get lucky, you might not, you know. But they have other names which are not the names that we're interested in. So it always makes me chuckle when I see a name that is clearly like the common name that someone's looked up. Now we're going to do the formulas. Remember, we have two rules for the formulas for ionic compounds. One is if our anion and cation have the same charge, the same size charge, they're going to combine 1 to 1. And if they have different charges, we're going to do crossover. Okay, how are we going to get the charges? Group 1A, Group 2A, and Group 3A metals form +1, +2, and +3 ions, and then Group 7A, Group 6A, and Group 5A form -1, -2, and -3 anions. So lithium's in Group 1A, so it's a +1, and then iodine is in Group 7A, so it's a -1. They have equal and opposite charges, so these guys are going to combine 1 to 1, and that'll just be Li, uppercase I. Rubidium is in Group 1A, so it is +1. Chlorine is in Group 7A, so it is -1. So again, they're just going to combine 1 to 1 because they have equal and opposite charges, RbCl. Magnesium's in Group 2A, which means that it has a +2 charge. And iodine is still in Group 7A, which means it has a -1. So in this case, they don't have equal and opposite charges, so we're going to be doing crossover. So we need 2 iodines and 1 magnesium, so it's going to be MgI2. Now, whenever we do crossover, we always want to check whether we've got the simplest ratio, and if we haven't, we can divide through by the smallest whole number. In this case, we can't simplify those numbers anymore. We never simplify the formula of a molecular compound. Only for ionic compounds do we divide through by the common multiple. Alright, let's move on to number 4. Below is the Lewis structure of the hydronium ion. Count the number of bonding pairs and the number of lone pairs around the oxygen atom. So the important thing here is that they're asking about pairs of electrons, and they're also asking about the oxygen atom. So they're not asking about individual electrons, they're asking about pairs. So bonding pairs are those that are shared, and in the case of the oxygen here, we've got 3 that are shared between the oxygen atom and the 3 hydrogen atoms. And then we have 2 electrons but 1 lone pair that are not shared, that are just residing only exclusively on the oxygen atom. So how many bonding pairs? 3 bonding pairs. How many lone pairs? 1 lone pair. Okay, so you want to be careful because you want to make sure that you're focusing on the correct atom, and also you want to make sure whether they're saying individual electrons or pairs of electrons. Okay, so just kind of take your time with it and read the question clearly. Okay, here we have another one. Count the number of bonding pairs and the number of lone pairs around the carbon atom. So it's focused on the carbon, and again it's pairs. Alright, so let's see what we've got. So there's my carbon atom, and then if I look here, I can see immediately that there are 0 lone pairs. I don't see any, but then the bonding pairs, I've got 1, 2, 3 bonding pairs going over to the nitrogen, and then on the other side of the carbon atom, I've got 1 bonding pair going over to the hydrogen. So in total, the bonding pairs is 4. So 4 bonding pairs and 0 lone pairs in this case. Not too bad. Just a matter of being able to read it. Okay, so this is about periodic properties again. So it says here we're going to be predicting the relative electronegativities of atoms. So electronegativity varies from francium to fluorine. It increases. Now, so what that means is basically it gets bigger as we go up a group and it gets bigger as we head left to right. So let's have a look and see what we've got. Now, you want to be aware that you can always just grab a table of electronegativities where you actually have the pooling values, and you can actually look these up and be very precise about it. But we're just going to follow the trend here, and we want to go from in order of decreasing electronegativity. So we want to go from highest to lowest. Okay, so let's see what we've got. So we've got selenium, sulfur, and oxygen. So what we see here is that we're going up a group, right? And what we know is that electronegativity increases as we go up a group. So we are going to write these in order of decreasing electronegativity. It's going to be oxygen, followed by sulfur, followed by selenium. All right, so now let's move on to the next ones. We've got fluorine, oxygen, and nitrogen. This is going across period 2. Fluorine, oxygen, nitrogen. And we know that electronegativity increases as we head to the right across the periodic table. So in order of decreasing electronegativity, it's going to go fluorine, then oxygen, and then nitrogen. Okay, because it increases left to right. Fluorine is the most electronegative element with an electronegativity of 4. Okay, we're moving along here. We're doing okay. What have we got here? Let's have a look. Predicting bond polarity. Okay, in each of the molecules drawn below, one chemical bond is colored red. Decide whether this bond is likely to be polar or not. If the bond is likely to be polar, write down the chemical symbol for the atom which will have the more negative charge. So again, remember, electronegativity increases from francium towards fluorine. So in this first molecule here, we're looking at the bond between 2 identical chlorine atoms. So what that means is that the difference in electronegativity will be 0 because there's 2 identical atoms. So that means that the highlighted bond, the one that's in red, is non-polar. So now I'm going to look at the bond between a bromine atom and a fluorine atom. Now bromine and fluorine are going to have different electronegativities, right? And fluorine is going to be more electronegative than bromine. So electrons are going to be getting pulled towards fluorine in that bond. And so that means that this bond is polar, and the more negative atom is going to be the fluorine atom. Now fluorine is always the more negative atom when it's bonded to something else. So fluorine goes in there. Okay, so the next bond, we kind of figured this out now, is the bond between 2 carbon atoms. And obviously the difference in electronegativity there will be 0. So this is going to be a non-polar bond. So the bond between 2 identical atoms is always non-polar. All right, now we're asked to calculate how many valence electrons are in the formic acid molecule. So every atom here is a representative element, and for representative elements, the number of valence electrons just equals the group number. So hydrogen's in group 1A, carbon is in group 4A, and oxygen is in group 6A. So we just got to add everything up. So I've got 2 hydrogen atoms that are in group 1A, and then I've got 1 carbon atom that is in group 4A, and then finally I've got 2 oxygen atoms that are in group 6A. So when I add all of that together, 2 plus 4 gives me 6, plus 2 times 6, which is 12. So 6 plus 12, that gives me 18 valence electrons in this molecule that are used to make all of the bonds in the molecule. And that would be the first step in drawing the Lewis structure of this molecule, would be counting up the number of valence electrons. Okay, let's have a look at this. Deciding whether a Lewis structure satisfies the octet rule. Decide whether these proposed Lewis structures are reasonable. Now, for a molecule or polyatomic ion to obey to be a correct Lewis structure, it has to satisfy 2 requirements. First, the number of valence electrons used to make all of the bonds and lone pairs has to be correct. And then secondly, every atom needs a noble gas configuration, which means that hydrogen gets 2 electrons, and everything else is 8 electrons. Alright, so that's what we mean by that. So it has to end up with an electron configuration like its nearest noble gas. So what we've got to do in every case, then, if we're going to check that the valence electrons are correct, we've got to add up the total number of valence electrons that each of these molecules or polyatomic ions would have if it has a correct Lewis structure, and then we've got to compare that to how many are in the structure. And then finally we've got to go through and check every single atom has either an octet if it's not hydrogen, or a duet if it is hydrogen. So let's give an example. The first one here, we need to calculate the number of valence electrons. So the formula is C2H-. So hydrogen is in group 4A, and carbon is in group 4A, and hydrogen's in group 1A. Here we go. So our number of valence electrons, we've got 2 times 4 for the carbons, plus 1 for the hydrogen, and then because we've added an extra electron negative to get the negative charge, we have to add 1 in. So 2 times 4 is 8, plus 1 is 9, plus another 1, we've got 10 electrons. So now I need to check how many electrons are actually in this diagram. So remember, every line counts for 2. So 2, 4, 6, 8. And then we've got, so that's from the bonds, we've got 8. And then we've got these guys that are in the lone pair plus 2 equals 10 electrons. So the valence electron count is correct. Now I have to check that every atom has a noble gas configuration. So hydrogen wants 2, and anything that's not hydrogen wants 8. So the hydrogen has 2, that's correct. This carbon in the middle here, we've got 2, 4, 6, 8, so that's correct. And then this carbon on the end, we've got 2 for the lone pairs, and then 4, 6, 8 counting off the bond, so that guy is correct. So this is a correct, good Lewis structure. Okay, so we can move on to the next one. So first thing we're going to do for the next one, find its formula, count up its valence electrons, and then compare that to the Lewis structure. So the formula here is CO2, and oxygen is in group 6A. So it's going to, each oxygen atom will contribute 6 valence electrons. So we get 4 for the carbon, and then 2 times 6 for the oxygen. So 4 plus 12, 16 electrons. Okay, so does our diagram have 16 electrons? Every bond counts for 2, right? 2, 4, 6, 8, 10, 12, 14, 16. So everything has the correct number of electrons. Now, before we decide that it's a good Lewis structure, we're going to check that each atom has either an octet if it's not hydrogen, or a duet if it is hydrogen. Now in this case there's only non-hydrogen atoms, so we're looking for every atom to have an octet. So 2, 4, 6, 8, the oxygen on the end there is good. Now we're going to do the carbon in the middle. 2, 4, 6, 8, the carbon in the middle is good, and then the oxygen on the end, 2, 4, 6, 8, it is good. So that is a good Lewis structure. Okay, so that was kind of easy. We haven't found any bad ones, so we don't have to just explain what's bad about it. All right, so the last one, again, we're going to begin by writing out the formula for it, and then we're going to do the electron count, compare that to the electron count, in this case, the polyatomic cation, and then we're going to check every atom has a noble gas configuration. So how many electrons have we got? Well, we've got, the formula here is CHO+. So we took an electron away to get the positive charge. For every positive charge that you have on your polyatomic ion, you've got to subtract 1 electron. So carbon's in group 4A, so that's 4 electrons for that guy. Hydrogen's in group 1A, so 1 electron for that. Oxygen's in group 6A, so 6 electrons for that. And then we're going to take 1 away for the positive charge. So -1 electron for every positive charge. So if it was +2, we'd take 2 electrons away. So 4 + 1 is 5, + 6 is 11, -1 gives me 10 electrons. So does it have 10 electrons? 2, 4, 6, 8, 10. It does have 10 electrons, okay? So it's passed our first test. Our second test is every atom needs a noble gas electron configuration. So hydrogen is going to want 2 electrons, and everything else is going to want 8. So hydrogen has a share of 2 electrons. The carbon, 2, 4, 6, 8, has a share of 2 electrons. And then the oxygen, 2 in the lone pair, and then 4, 6, 8 for the 3 bonds. So every atom has an octet. So as long as it meets those requirements, that the valence electron count is correct, and every atom has a octet or duet, then we're good. So this is also a good Lewis structure. There we go. All right. So, it shouldn't be too hard if you've, if you do find a problem, it should be obvious. It's going to either be one of those things. There'll be a problem atom that doesn't have an octet, or there'll be, the wrong number of valence electrons. Okay, so now it says predicting the single bonded molecular compounds formed by 2 elements. So when 2 nonmetals come together, what they're going to do is they're going to form a molecule. So a molecular compound forms between 2 nonmetals, and it can even be 2 nonmetals of the same type of atom, like 2 hydrogen atoms, for example. So a nonmetal with a nonmetal will form a molecular compound. So nitrogen is a nonmetal, as is fluorine, so that will form a molecular compound. Hydrogen is a nonmetal, as is bromine, so that will form a molecular compound. Sodium is not a nonmetal, so we don't have to do anything for that line. So that was kind of cool. It's always nice when there's like one line in the table that you don't have to do anything for. All right, so now we have to predict how these atoms are going to come together. And the key here is to recognize that the number of unpaired dots in an atom's Lewis symbol is the number of bonds that it likes to make. So hydrogen is in group 1A, it has 1 valence electron. So every element that is in group 1A has a Lewis dot symbol with just 1 dot. When I go over to group 4A, every element that's in there, you guessed it, gets 4 dots. When I go over to 5A, you guessed it, every element in there gets 5 dots. And when I go over to 6A, 7A, and so forth, they get, 6 and 7 dots respectively. So 6A is going to look like 1, 2, 3, 4, 5, 6. That'll be for anything that's in 6A. And then anything that's in 7A will get 7 dots. 1, 2, 3, 4, 5, 6, 7. Now, what we want to be on the lookout for is these number of unpaired dots that's around the symbol indicates the number of bonds that it likes to make. So nitrogen's in group 5A, so it gets 5 dots. 1, 2, 3, 4, 5. And then fluorine is in 7A, so it gets 7 dots. 1, 2, 3, 4. Oh, I'm kind of doing this a little inappropriately because I know the answer. You should always put the dots singly first. So we want 7 total dots. 1, 2, 3, 4, 5, 6, 7. There you go. So nitrogen likes to make 3 connections and fluorine likes to make 1. So we're going to need 3 fluorines. Okay, let's move that nitrogen. Oh gosh, we're going to need 3. And then the nitrogen is going to go there. There we go. And you see these unpaired dots are going to pair up and form our single bonds. So the chemical formula will be NF3. Okay, so how do we name it? Well, remember when it comes time to naming molecular compounds, we give the name of the first element unaltered. So it's just going to be nitrogen. And then we give the name of the second element, but we change the ending to IDE, so fluoride. Now, if you're a little shaky on the stem names, remember you can just look them up in a table, and that table's in your book. Then we apply prefixes. There's a slight rule that we have to be aware of here, is that we don't use mono if there's only one of the first atom. So it's not going to be mono nitrogen, but it is going to be trifluoride. So the first one there is going to be NF3 for the formula, and then nitrogen trifluoride will be the name. Okay, let's have a look at the next one. So we've got hydrogen. Hydrogen likes to make 1 bond. And then we've got bromine. Bromine's in group 7A. So 1, 2, 3, 4, 5, 6, 7. And so they both like to make 1 bond. So just 1 hydrogen is going to take care of this. So the formula will be HBr. Now, when our compound begins with hydrogen, we don't use Greek prefixes. So that's another rule. So this is just going to be called hydrogen. And instead of it being monobromide, it's just going to be called hydrogen bromide. So there's a couple of little things there. When we have just one of the first atom, we don't call it mono. But when our formula begins with hydrogen, we don't use Greek prefixes at all. We name it almost as though it was like an ionic compound. All right, let's keep going. Predicting the compound formed by 2 main group elements. So the main group elements are those that are not transition elements and are not inner transition elements. They're the ones that poke up a little bit higher on the left and the right of the periodic table. And there are 2 types of compounds that we might see. There are the combinations of nonmetals with other nonmetals, and we call those molecular compounds. And then there are when metals combine with nonmetals. Okay, and we call those ionic compounds. Now, what if a metal combines with a metal? Well, it's going to be neither molecular nor ionic, right? So that's ionic, and then these guys molecular. molecular compounds are also referred to as covalent compounds. So all we have to look at is where are these elements on the periodic table. If I've got a metal with a nonmetal, it's ionic. If I've got a nonmetal with another nonmetal, it's molecular. And if I've got two metals together, then it's neither of those things. So let's see what we've got. So fluorine is a nonmetal. There we go. And sodium is a metal. So this guy is ionic. Sodium, as we've said, is a metal. And then immediately under sodium is potassium. So we've got two metals. So that means it's neither ionic nor molecular. And then finally we've got oxygen over in group 6A with magnesium in group 2A. So that's a metal with a nonmetal, and so that makes that ionic. So now we have to work out the chemical formula. So what we've got to do is, because these are ionic compounds, we've got to consider charges, right? And remember, if they have the same size charge, they're going to be a 1-to-1. If they're different, we're going to do crossover. So what do we know about the charges? Well, we go, it's +1, +2, +3, and then it goes -1, -2, -3. So we just got to find where everything is in the periodic table, right? So our metal goes first, sodium, and it's going to be +1, and then fluorine over here, so it's going to be -1, so they have the same size charge, so they're going to come together 1-to-1. Okay, what's next? Well, the next one is, and we don't have to do anything for this, right? And that's done, is oxygen with magnesium. So magnesium is our metal, Mg, and as mentioned previously, it's in group 2A, so it's 2+. And then the ion it's being combined with is oxygen, and that's in group 6A, so it is 2-. So again, they have the same size charge, same size, opposite sign, so they come together 1-to-1. So that was like, not too bad. Okay. Now we have to do the full deal of drawing a Lewis structure, and we're also asked to include any resonance structures. Okay, so the first thing I see is that it's an anion, so I'm going to have to add electrons equal to the charge. So always add 1 electron for every negative charge when you're calculating the number of valence electrons. So we've got carbon over here, hydrogen, oxygen. So carbon's in 4A, oxygen's in 6A, and hydrogen is in 1A. So let's add up the valence electrons. So we've got 4 for the carbon, we've got 1 for the hydrogen, we have 2 oxygens, so 2 times 6, and then we have 1 for the negative charge. Okay, so what is this going to be? 4 plus 1 is 5, plus 12 is 17, plus 1, I've got 18 electrons. So I'm going to keep a note of that up here, 18 electrons, which I'm going to use to do all the work with. So now, what atom is going to go in the middle? Well, we know a few things. Is that hydrogen never goes in the middle, it's always an outer atom. And then our rule for deciding the central atom is it's the one with the lowest group number. So carbon has a lower group number than oxygen, so carbon's going to go in the middle, and then we've got oxygen, oxygen, hydrogen. We want to put the whole thing in parentheses with a minus sign there. So what I want to do now is deduct the number of electrons just used to get the basic structure. 2, 4, 6. So take away 6 electrons from my total, leaves 12 remaining. And then I work from the outside in, completing octets. So hydrogen is happy with its share of 2 electrons, but the oxygens need 3 lone pairs in order to get up to an octet. So I added 6 electrons to each of the 2 oxygen atoms, so that leaves me with 0 electrons left. So if I had electrons left over at this point, I would put them on the central atom, but there's none left. So now what I have to do is check whether the central atom has an octet, and it doesn't. 2, 4, 6. It only has 6 electrons around it. So I have to bring in one lone pair to get it up to 8. So you can see that I have two choices. And so that's why they talk about resonance structures here, because I'm going to need to draw one Lewis structure that represents each of the different ways that I could have moved those lone pairs around to give the carbon an octet. So you can see that one way I could do it would be moving in a lone pair here to put a double bond there, or the other way I could do this would be bringing in a lone pair here, and then that would become the double bond there. So that's what we're talking about when we're saying we have multiple resonance forms here. In reality, what does it look like? It's a hybrid of both of those resonance forms, but we don't have a good way of drawing that, so we draw out the two resonance forms. Alright, this is going to be fun. I just want to grab a little thing here. I'm going to grab this guy. So, there we go, that'll do. So, in this question, what I'm asked is to predict the bond angle in a molecule. All right, so it says, what is the angle between two of the carbon to chlorine bonds in the carbon tetrachloride molecule? So before you can do this, you need a Lewis diagram. So carbon's in group 4A and chlorine is in group 6A. So I'm going to count up valence electrons. So 4 for the carbon, and then I got 4 lots of, so chlorine is in group 7A. 4 times 7 for the chlorine. So 28 plus 4 gives me 32 electrons. So because carbon is in 4A and chlorine is in 7A, what that means is that carbon will be the central atom and the chlorine atoms are going to be on the outside. So what I'm going to do now is I'm going to deduct the electrons that I used to make those 4 bonds. So I've got to take away 8 electrons, 2, 4, 6, 8, and that means I've got 24 electrons left to finish off the Lewis structure. So now I have to complete the octets on my outer atoms, which in this case means I'm going to have to put 3 lone pairs on each of the chlorines. There we go. So now every outer atom has a complete octet. So what I've got to do then is I've got to deduct how many electrons I used to complete those octets. So there were 4 chlorines and I put 3 lone pairs or 6 electrons on each one. So that means that I actually have 0 electrons left. Okay, so now I just check the octet on my central atom. If I did have electrons left over, I would place them on the central atom, but I don't have any. So I'm just going to check its octet, 2, 4, 6, 8. And everything is good. So that Lewis structure is done. So now the question becomes, what is the angle between 2 of the carbon-chlorine bonds in this molecule? So what is this angle in here? Okay, so how I figured that out is by using one of these VSEPR tables, and I just like Google VSEPR table, and this is like the most popular one. And so how many electron groups do I have around my central atom here? Well, an electron group is either a lone pair, which we don't have any on, or a bond of any type. So I've got 1, 2, 3, 4 bonds. So this has got 4 electron groups, which means it has the tetrahedral bond angle of 109. And the actual correct number is 109.5, but if you put 109, I'll give it to you. All right, so that's going to be the angle, 109.5. All right, so moving right along. I have to pause for one. Okay, I just had to pause for a moment there because my computer needed to sync to the internet. Alright, here we go. Oh, no, and it's still unhappy. Let me see if we can get this to restart again. Here we go. The joys of being online. Here we are. Alright, moving on. Yay, it advanced. Okay, so let's see what we've got here. This is asking us to predict whether molecules are polar or non-polar. So what one needs to do for this is to draw a Lewis diagram for the molecule, and then you're going to have a look at that molecule and see if you have asymmetry around the central atom. And by asymmetry, what we mean is that there is multiple different kinds of things attached to that central atom. So Lewis diagram for everything to begin with. So we've got this molecule here, carbon disulfide. Carbon's in group 4A, sulfur is in group 6A. So let's count up valence electrons, 4 for the carbon and then 2 times 6 for the sulfur. So 4 plus 12 gives me 16 valence electrons. So what I have to do now is ooh, that was unexpected, is figure out the shape of it, right? So carbon goes in the middle because it's in group 4A, and then we've got sulfur attached either side. So to get this basic structure, we used up 2 4 electrons. So we've got to take away 4, that gives me 12 electrons to finish everything else off. So now I complete the lone pairs on each of these, complete the octets on each of these sulfur atoms by adding 3 lone pairs to each. So that uses up 2 times 6 electrons, use up 12 electrons, so I got 0 electrons left. So now I check the octet on my central atom, and I've got 2 4 electrons around that carbon, so I'm going to bring in 2 electrons there, and then I'm going to bring in 2 electrons there, and that's going to give that central carbon a complete octet. So when I look at the central carbon, it only has one kind of thing attached to it, which is a sulfur atom. So this guy will be non-polar. So that's good because then I don't have to worry about what atom is closest to the negative side of the molecule. So now we can move on and start work on the next one. So the next one is HCl. So hydrogen's in group 1A, contributes 1 electron, and then chlorine is in group 7A, so that means it's going to contribute 7 electrons. So I've got 8 electrons total to do this. So I'm going to put, obviously the pattern of bonding when there's 2 atoms, they're just joined together by a single bond. So that's going to use up 2 electrons, which means I've got 6 electrons remaining. So now what I've got to do is to complete the octet on all of my atoms. So I'm going to start from the outside in. Now hydrogen is happy, so I'm just going to leave that be, but chlorine only has 2 electrons. So it needs to add another 6, and that finishes off all of my electrons that are available. Now every atom has its noble gas configuration. So hydrogen has a electronegativity of 2.2, and chlorine has an electronegativity of 3.16. So that means that this bond will be polar, and the chlorine end will be the negative end, and the hydrogen end will be the positive end. So this is going to be a polar molecule, and chlorine will be the atom closest to the negative end of the molecule. Not too bad because it was just a diatomic molecule. Pretty easy to figure out what was going on there. Alright, let's move on and do the next one. Silicon tetrafluoride. I like to say the name sometimes when I read the formulas. It helps me with the naming of things. So silicon is in group 4A, just underneath carbon, and fluorine is in group 7A. And I'm kind of thinking fluorine is the most electronegative element on the periodic table. It's way more electronegative than silicon, but that doesn't mean that it's going to be polar. So silicon's group 4A, so contributes 4 electrons, and then I've got 4 fluorines, and each of them contributes 7 electrons. So 4 times 7 is 28, plus 4 is 32 electrons. So silicon has a lower group number than fluorine, so it's going to be my central atom. So it's going to be silicon with the 4 fluorines attached like so. So to attach the 4 fluorines, it requires 4 single bonds or 8 electrons, and that leaves 24 electrons left to finish everything off. So each of my fluorines has at the moment only 2 electrons, so it's going to need another 3 lone pairs or 6 electrons to finish off the octet of each of those fluorines. There we go, just like that. So 4 times 6 is 24, right? So now I got 0 electrons left. So the only last thing to do is to check that I have an octet on my central atom. 2, 4, 6, 8. I do. So that is a great Lewis structure. We've got everything figured out. So now I have to decide, is it polar or non-polar? Well, when I look at that central atom, it's got no asymmetry about it. Everything attached to that central atom is exactly the same. All of the atom types attached are of the same type, and there are no lone pairs. So this is non-polar, and I don't have to decide whether there is a polar or negative end of the molecule, so I don't have to worry about the last column. Alright, cool. So now let's just have a look at the 10 questions in the quiz. So there's quite a few problems here where these seem to be in, yeah, it seems like we have 2 copies of question number 3, so we're going to pick up a question number 2. Alright, so this is just kind of a repeat of what we just had, isn't it? Decide whether each molecule is polar or non-polar. If the molecule or polyatomic ion is polar, write the chemical symbol of the atom that's closest to the negative side. So that's pretty easy. So what do? Lewis structure of each molecule, and then we are going to, from there, we'll decide if it's polar or non-polar. Alright, so let's get going with the Lewis structure. So H2S is our first one, so hydrogen's in group 1A, sulfur is in group 6A. So there it is there, hydrogen and sulfur. So let's go. So 2 times 1 for the hydrogen, and then 6 for the single sulfur. So that gives me a total of 8 electrons. So hydrogen is never the central atom, which means that sulfur must be. There we go. So connecting each of the 2 hydrogens uses up 4 electrons, and that leaves 4 electrons for everything else. So I'm going to complete the electron configuration of my outer atoms, and in this case, hydrogen is happy because each hydrogen atom has 2 electrons around it. Now I'm going to put my leftover electrons as lone pairs on my central atom. So minus 4 electrons, and that gives me 0 electrons. And then I double check that my central atom has enough electrons around it. So we've got 2, 4, 6, 8. It's good, so that's a good Lewis structure. So now I've got to decide, is it polar or non-polar? So the first thing to recognize is that this guy here has more than one kind of thing around the central atom. So that, because it's got lone pairs and it's also got hydrogen, so there's asymmetry about the central atom. So that means that this molecule is polar. Now I have to decide what end of the molecule is going to be more negative. So to think about that, I have to think about its shape. And this guy has 4 electron groups, and 2 of them are lone pairs. Okay, and when we have 4 electron groups with 2 lone pairs, we end up with what we call a angular or bent shape to where the atoms are, right? They look kind of like that. It's the tetrahedral angle here because we've got a total of 4 electron groups, but the atoms are kind of in this inverted V shape. So that's important. And then we have to think about electronegativities. So hydrogen is way over on the left of the periodic table and sulfur is way over on the right. And we know that electronegativity increases towards the top of the periodic table and also towards the right. And if you look up the values, you'd see that sulfur is far more electronegative than hydrogen. So all of the electrons are getting sucked towards the sulfur. So that means that the sulfur end of the molecule is a little bit positive and the hydrogen end of the molecule is a little, the sulfur end is a little bit negative and the hydrogen end is a little bit positive. And so overall kind of electrons are getting pulled up in this molecule. If you want, you could put it through there like that. So the atom that is closest to the negative side of the molecule is going to have to be the sulfur. Okay, so there we go. All right, now let's kind of speed this up a little bit with the SiF4 because we've already seen it and we're kind of running out of time. So let's have a look at the SiF4. So the Lewis structure looks like this. Won't bore you with writing that out again. So what that means is that when we look at the central atom, there's only one kind of thing attached to it. It's completely symmetric. So this guy is nonpolar. Now again, I'm going to kind of hustle a little bit just to kind of focus on the important parts here. In hydrogen bromide, the Lewis structure, we have a hydrogen atom attached to the bromine atom via a single bond, and there are 3 lone pairs on the bromine. So the important thing to recognize is if I look up the electronegativities of these 2 atoms, I realize that bromine is more electronegative than hydrogen, which means the hydrogen end of the molecule is a little bit positive and the bromine end is a little bit negative. So this will be polar because we've got 2 different atoms connected by a single bond, and the bromine will be closest to the negative end of the molecule. Alright, so unfortunately we're kind of running out of time here, so I'm going to wrap things up here. We didn't quite get through everything as intended, but I think you have a lot of example problems there, and that'll be enough to kind of be getting going with. So I hope you found that helpful.